I did point out in the last video that the videos on vibrating mass spring systems are based upon notes that you find on the webpage for the course. And I said that that comes from a book that I've written on differential equations, hence the funny numbering. This is chapter 5 in the book, and so that's why you're seeing chapter 5 rather than chapter 15 like in the textbook or calculus, right? Last time we talked about undamped, unforced. What I would like to do in this particular section, I talked about damped, but still unforced. And in the last video, we'll get around to talking about force motion. And that's important because it leads to a concept called resonance, which is really important in applications of vibrating masses or vibrating anything. So undamped, okay? So a differential equation is going to be m d squared x dt squared. Now we're putting in damping, beta dx dt. The spring is still there, kx, but no other ones, so we're putting a 0 there. The f of t is 0. So we're again solving a linear, homogeneous, constant coefficient differential equation. And along with it will be coming initial conditions in order to get the motion initiated. So let me take some examples. Right? And I think you could agree that we thought about it for a second before we get started. Once you throw damping in, various scenarios could occur. Energy is going to be lost during the damping. So you can't have simple harmonic motion. That's impossible. But if damping is very small, I can envision I'm getting oscillations that would gradually die out. On the other hand, if damping is really severe, perhaps we've got this spring and this mass, and it's all inside a container of molasses. Well, I think damping would be very severe, and I think therefore I'm unlikely to get oscillations. If I pull it down and let it go, I think I would just go slowly back up into its equilibrium position. So the amount of damping will seriously affect what kind of motion we're going to see. And we're going to see 3 types. One is called underdamped, one is called overdamped, and one is called critically damped. So I want to do 3 examples to illustrate those 3, and then do like I did last day, give a general discussion for all m, beta, and k. So I'm going to choose the same m that we did last day. I'm going to choose the same k last day. And I'm going to put beta equal to 2 for our first example. So that says the damping force is twice the velocity. Right? Twice the velocity. So if we put that in, let's put on some initial conditions. Initial conditions. All right, let's say x at 0. Let's pull it either below or to the left, depending on whether vertical or horizontal, 10 centimeters, right? And let's give it no initial velocity. X primed at 0 is 0, right? So we move it 10 centimeters away from equilibrium and we let it go. So we're going to solve this. So auxiliary equation is 2m squared. Beta is 2m, and 1250 is equal to 0. Divide out the 2's, m squared, m, and 625. Doesn't factor, quadratic form, minus 1, plus or minus, square root of b squared 1 minus 4ac. 4 times this. Is that 2,500? All over 2. So, minus 1/2, plus or minus the square root of 2499 over 2i. Complex roots. Therefore, our theory says that x of t is going to be equal to e to the minus t over 2. C1 be cosine of the square root of 24, 99 over 2t. C2, the sine of the square root of 24, 99 over 2t. So there's our general solution of the differential equation. We have to force on the initial conditions. Minus 1 over 10 is equal to when you put in 0. If I put in 0, that one's 1, that one's gone, that one's 1, so C1. So there's C1. Initial velocity was 0. I have to differentiate this, put it in 0, and equate it to the 0. So differentiate, product rule. That one times the derivative of this one, and then we put in 0. So if you differentiate this, down comes a half with a minus sign, right? And then you put in 0 here, you're going to get 1. And this one is C1. So there's that one times the derivative of that one at 0. Now we need this one times the derivative of this one at 0. All right? So this one at 0, that's 1. Differentiate this, put in 0. Differentiate this, turn to a sign, put in 0, 0. Differentiate this, we would get 24, 99 square root over 2, C2, and a cosine there. So there's C1, and the second one is going to give me C2. So C2 then, C2 is equal to 1/2 of C1, which is minus 1/10. That one there, okay? Sign. Okay? I want to take that one over there, so it'll be a 1/2 with a plus sign. And then I put it on. Okay. And then a 2 over the square root of 24, 99. How does that look for C2? Cancel, cancel. So there it is. So x of t then is equal to e to the minus t over 2. C1 minus 1 over 10. The cosine of the square root of 24, 99t over 2, plus C2, which is a minus 1 over 10 square root of 24, 99, the sine of 24, 99 over 2. There. All right. So there then is the displacement of this mass. Same mass, same spring, but now we put in some damping. Graph. What does it look like? Do you agree? I could take this part without him, and I could rewrite it just like I did for the undamped stuff. I could write this as a sine or cosine, sine of the square root of 24, 99 over 2t plus 5. All right? And so I'd have then up front this e to the minus t over 2. And I know a is the square root of this one squared plus that one squared. That's the formula for the a. Right? Picture. What does it look like? Well, this part here, inside here, that's simple harmonic stuff. There would be its amplitude, but what does this do? This is killing that amplitude as time progresses. So what would the picture look like? Where did it start? This was the initial displacement. Down here at minus 1 over 10. And then I let it go. Then it's going to go up, right? So it's going to go up. So here it comes. Right. There it is. Right. It's that simple harmonic motion, but the amplitude keeps getting squashed. Is it periodic? No. It does happen, though, the following. Right? If you take the distance between here and here, time-wise, take that, right? And then you do it to the next one, and you do it to the next one. Or you take the distance between this minimum and that minimum. Or this minimum and that minimum. Or if you take the distance between here and here, it's always the same. People call that the quasi-period. Because it's not really a period, because we don't have periodic motion, but those distances are always the same. In addition, right, if I were to draw just that, it would be simple harmonic motion, and this thing is squashing it. If I put on here a picture of e to the minus t over 2, then it would come down like this. And if I put on e to the minus t over 2, it would come in here like that. So that's a picture of this one, and this one's a picture of minus the right. So this curve comes up and periodically touches that. Well, I also need here the A, and A. Right? So that's bounding those oscillations. This is called underdamped. Motion. Or oscillations. Right? Underdamped. You'll see why they chose that terminology shortly. Is everybody happy with that one? Well, let me now increase the beta tremendously up to 120. Right? So now the damping is 120 times the velocity. That's a lot more damping than what we saw here. Let's see what effect that has. Oh, we'll go through the same thing. Yes. Auxiliary. It is again 2m squared plus now 120m plus 1250 is equal to 0. Divide out the 2's, m squared, 60m, and 625 is equal to 0. Just factor m equal to minus 60 plus or minus the square root of b squared 3600 minus, didn't we see that one before, it was 2500 all over 2. Therefore minus 30 plus or minus, oh, this is 1100. How about 10 and therefore 5 root 11? How does that look? Now we've got 2 real roots. So therefore, x of t is not going to involve sines and cosines at all, because we've got real roots. So, and solutions, C1, e to the minus 30 plus 5 root 11t plus C2 e to the minus 30 minus 5 root 11t. So there's my solution now. All right. Now, a point of interest. Okay? Do you think this term, this number in here, is positive or negative? And the answer, you should say it immediately. It's got to be negative. If it weren't negative, right, this one is certainly negative. So it means as time progresses, this is going to get smaller, 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 smaller. If that baby were positive, that's going to be very strange. It's going to say, actually, man, you're getting large. So anybody who writes a number in here that's positive, maybe they kind of blew this calculation, right? And didn't check here. 5, square root, that's about 3, that's about 15. Good, that's negative, okay? But if they had something in here that's positive, let's say, you are not thinking at all. There's no way that that could be a positive number. So it's a slight check on your calculations. We have to force on the initial conditions of minus 1 over 10 is C1 plus C2. That's the initial displacement. Then we've got this initial velocity, that 0 is equal to, and I have to differentiate this and put in 0. Minus 30, 5 root 11, when you differentiate C1. Minus 30, minus 5 root 11, C2, when you differentiate and put in 0. So now you have to solve these two equations for C1 and C2, which I don't want to do. So, for C1 and C2. What I would be interested in, and I don't want to do it here, or this particular one, I would like us to draw a picture of what the possible scenarios here are. What is that thing going to look like? And I suggest there are two scenarios in general. So what do we do? We started it down here, and we let it go, right? We let it go. Its initial velocity is 0. So the graph is going to come out here kind of horizontal. And then what's it going to do? Do you, for instance, think that it could come up here and cross the t-axis? Do you think that could happen? And I don't think that can happen. I think this particular one has to look like that. I don't see any other possibility of that happening other than that. Okay? In general, however, what might happen, right? And to me, it depends upon where I started from and with what velocity. So let's make sure I say that one is this one. Right? Now let me say all other possibilities. We give it, say, an initial displacement x0. If we were to give it a small velocity as well, do you think it would look like this? Giving it a small velocity, the initial slope is negative. I think that's what would happen, right? But suppose I give it that same initial displacement, and I take a sledgehammer to it, and I give it one tremendous whack. Now I can either tremendous whack that in the positive direction or the negative direction. If I hit it with a positive velocity, here it goes, up it goes, then it's going to go up and it's going to come down. Do you think it's going to cross this axis? The answer is no way. It's going to go like that. And I don't care how hard you hit it. It's going to go up and it's going to come down. But suppose I gave it a huge whack downward. If I gave it a little whack, then it's this one. If I gave it a huge whack, I think I could force it through the equilibrium position. And then it's going to simply come up and go like that. All right? Those are the only possibilities for what could happen in this scenario. This is called overdamped motion. Damping is so severe, it's completely squashed all oscillations. And it can pass through equilibrium at most once. And that depends upon what the initial displacement is and what the initial velocity is, whether it does it or whether it doesn't. Right? So there's the second possibility. Third possibility, I'm going to put beta equal to 100. Less than the first, or more than the first, and less than the second. And do the same initial conditions. They don't change much. So now the auxiliary is 2m squared, and we have 100m, and we have 1250 equal to 0. Divide out the 2, m squared, 50m, 625 equal to 0. Now it factors to m plus 25 squared. So m is equal to minus 25, minus 25. So x of t this time, we have a repeated real root. So therefore, C1, C2t, e to the minus 25t. And again, there's no way that that guy can be positive. Don't ever give me a positive guy there. Initial conditions, minus 1 over 10, equal to, put in 0, C1. 0, differentiate. X prime is 0, 0. Differentiate. This one times the derivative of that one at 0. Minus 25, C1, plus this one times the derivative of this one at 0, C2. And so now you can get C1 and C2. What does this look like? What does a graph of this thing look like? And the answer is, it basically has the same possibilities as you saw here before I erased it. For this particular one, right, we started down here at minus 110. And we gave it some velocity, and it's going to go like that. But the velocity gave it was 0, so it's simply, I should press draw it like that. Since the initial velocity was 0, it should come out here horizontal and then go like that. But I've got other possibilities depending upon what this one is and what this one is. I could have the possibilities that I saw here. They're all possible. It can go through equilibrium, but it can only do so at most once. Right? This one is called critically damped. Critically because any increase in beta, anything bigger than 100 is going to force it into overdamped. Anything less than 100, and I'm going to get underdamped, and I'm going to get oscillation. So this is the dividing beta between over and under damped. Clear? So we got 3 possibilities then that you have. Let's talk about a general discussion. General discussion. We're looking at m d squared x dt squared, beta dx dt, and kx is equal to 0. Unforced but damped oscillations. Auxiliary equation, m squared, beta, wrong one, big M, little m squared, beta m, and k to 0. Solve it. M minus beta, plus or minus the square root of beta squared minus 4km all over 2m. And you can see that because you had a quadratic, you've got these 2 roots, and everything depends upon this guy. Whether he's positive, whether he's negative, or whether he is 0. So case 1, that beta squared minus 4km is less than 0. Which means then, if this is happening, it says, this is for, say, smallish beta, okay? Because if this is supposed to be negative, then we're talking about this guy being bigger than this guy, which means then for smallish depth. In that case, then what do you got? M is equal to minus beta over 2m, plus or minus, and now that guy's negative, and we want to write this. How about I write this? 4km minus beta squared over 2m with an I. Is that what you would write if that thing under the discriminant, or that thing underneath the square root sign, is negative? The answer is yes. And so now x is equal to e to the minus beta t over 2m, C1 the cosine of the square root of 4km minus beta squared over 2m times t plus c2, the sine of the same thing. And what do we got then? Underdamped. So this is the underdamped. When beta is smallish. Well, second possibility, that beta squared minus 4km is 0. In that case, what do we got? That m is equal to minus beta over 2m repeated. Minus beta over 2m. Now, this square root has gone away, and you're getting a repeated root. This time then, x of t is equal to c1, c2t, e to the minus beta t over 2m. And what do I got? Critically damped. And finally, the third case, when that beta squared minus 4km is positive. That's greater than 0, that means you've got a large amount of damping. So now, if this thing is positive, then we've got two real roots, and x of t then would be equal to c1 e to the minus beta plus the square root of 4km. Wrong way around. Beta squared minus 4km. That multiplying t divided by 2m. That's for one of them. Plus c2 e to the minus beta minus the square root. And this one is overdamped. See, that we'll always get one of those three cases. Critically damped, overdamped, underdamped, and it all depends upon the sign of that thing there. How big the damping is relative to the product of K and M. So next video, bring in forces.